The heart is one of the most vital organs in the human body and is part of the cardiovascular system. And its primary function is pumping blood to the rest of the body to ensure constant circulation via an extensive network of blood vessels. A good way to visualize it is by drawing an analogy between the heart and road traffic. Let's say the body is a city and the heart is the downtown. Blood traveling in our body is subject to resistance, which could be computed as follows. Where L is the length of the vessel, N is the viscosity, and small r is the radius of the vessel. So if you were to think about it in terms of roadwork, in terms of our analogy, then resistance is a factor that would delay delivery of cargo on time or even completely. If the destination is too far away, so in this case L is very large, then the car would take a lot of time to get there. So that means it increased resistance. If the road is narrow, so small r is very small, then there will be more traffic and so greater resistance. Let's take the example of these two blood vessels. In the first example, we have two resistances, resistance 1 and resistance 2. The total resistance would just be R1 plus R2 because they are put in series. However, in the second example, we can see that we have 4 different resistances and they are put in parallel. Then that would mean to compute the total resistance, it would be 1 over the R total being equal to 1 over R1 plus 1 over R2, 1 over R3, and 1 over R4. And that would give us the C total to be simply C1 plus C2 plus C3 plus C4 because recall that C is the reciprocal of R. Well, that sounds great. However, how do labs study the physics of the heart so accurately, and how do they determine such physical relations? Well, biomedical engineers rely on what's called physiological modeling. Physiological modeling is the process of constructing a model that predicts the outputs of biological systems as a variation of altered inputs based on different parameters. And physiological models can actually come in different varieties. They can be conceptual, mathematical, computational, physical, or even animal. One of the methods to construct an organ model is by using what's called finite element modeling, where an organ's geometry is broken down into simpler elements such as tetrahedral or quadrangle-shaped elements, where each element is studied individually by finite element analysis, or what's known as FEA. In order to construct this, we need 5 key inputs are required. The first one is geometry. In this case, we aim to construct a solid model by adding individual layers of images. The second one is mesh. We aim to break down the solid model into discrete elements. Third one is material properties, and we aim to discern the inherent mechanical properties of the material to be used. Fourth one is boundary conditions. We want to understand the boundaries of the model as accurately as possible. And the fifth one is loading conditions, where we want to understand and simulate the forces it is being subjected to. Now, let's take a look at how finite element modeling can be used in order to model a heart. Let's take, for example, this research paper done by Zhang and Bajaj titled Finite Element Meshing for Cardiac Analysis, and it's been done in the University of Texas at Austin, where the authors developed a technique to produce a tetrahedral finite element mesh model of a human heart. Another schematic from the research paper would be this figure. Part A is the heart model viewed from the outside, whereas Part B is the result of boundary detection in wireframe, and Part C is a cross-section of the adaptive tetrahedral mesh. So in this video, we talked about resistance, compliance, and the relationship between viscosity, length, and the radius of the vessel In addition, we took an introduction to finite element modeling, which is a part of physiological modeling, and we saw an example on how we are linking both subjects. I hope you enjoyed this video, and thank you so much for your time.